Hi everyone, we are on the Promenade des Anglais in Nice, which is a famous promenade where people walk around, go to the beach and swim. The temperature is still good. And we are making a break on our NEO-MAPP meeting. We are preparing to save the world from an asteroid impact. And for that we need also to relax some time. And this is a promenade, and we are actually expecting what we call the French patrol, which are the military jets that should come and make a little show over the program, over the promenade for the young children, which are in a hospital. So we have a great opportunity to enjoy the nice weather of the Côte d'Azur, which is always like that, and therefore that's also good for the brain to cool down before starting again to work.
Do you want to introduce some of the team members?
Yeah. So here you have Dr. Zhang, who is a postdoc of NEO-MAPP, and she's a specialist of modeling of asteroids, in particular their internal structure, their structural evolution, and also what happens when there is an impact on an asteroid, what kind of crater we can make, which is a very complex problem and very relevant for planetary defense, because we try to predict how much deflection we will do if we do an impact on an asteroid. So Yoon is doing all the numerical models for that.
Yeah.
Hello Yoon, how are you?
Hi, I'm very good. Yeah.
Good?
We would like to practice how to defend the asteroids in computer first, and then we will have better chance when these things will happen.
Exactly, and we'll be able to verify our computer simulations by an actual experiment with a DART impact, which will make an impact on a small moon of a binary asteroid. And with the Hera mission from ESA, we will also measure the crater size and therefore check whether Yoon is right or wrong in her simulations, which is always good to know. Let's go again in the impact field. We have two experts of impact physics, Martin Jutzi and Sabina Raducan from Bern University. So Sabina is a postdoc and Martin is now a professor, University of Bern. So, and they are specialists of the fragmentation of rocks. So what happens when we impact at high velocity a rock, how it fragments, how it becomes hotter, and then what happens to the fragments later. So Martin, welcome to the team.
Thank you.
So where are you exactly working?
Where I'm working? I'm
Yeah.
working in Bern.
In Bern?
It's not quite as nice as Nice, still a very good place.
Yeah, but Bern is where one of the what we call hydrocodes, which are the impact physics code, was developed initially.
Yes, and now it's actually the name of the code, thanks to Sabina, is Bern's SPH code.
Bern's
so
SPH
that's now the standard code for this sort
You
of
know,
things.
we have the Nice model for planetary formation. You
we
have the
have
Bern SPH code.
Yeah, for asteroid destruction.
Asteroid destruction.
Yes.
Yeah, this is a very good code,
Yeah,
and
and
Martin introduced a lot of physics in it.
Yes, and Sabina is testing it carefully and to make sure that it works. So we have plenty of experiments and
Okay.
making
So
sure it's going well. Yes.
good. So if it's wrong, it's your fault.
Well,
That-
I'm trying to break
yes.
it, but I didn't manage it.
I imagine. But you do also another kind of codes, right?
Yeah, I also work with ISAD, which is developed in London and in Berlin.
So there are different ways to simulate an asteroid impact, and the problem is we need to make sure that these different ways are consistent, give the same results. Otherwise we have a problem because there is only one physics. So it's good to have two people experts in two different kind of codes, so they can agree or disagree, eventually agree, I hope. So that's
We're
a
working
great
on that,
combination.
yes.
Yeah, we're working on that. Okay, so let's see. Here is another crazy guy. So this is Alain Herique. You can immediately see what I mean. Hello, Alain. So Alain was a comet guy first. He was working on Rosetta. What did you do in Rosetta?
Contribute to the concept experiment, which is the first experiment to probe the internal structure of the comet. It's a radar using the lander, Philae, and the orbiter. And the idea was to determine the internal structure and the composition, not close to the surface, but at a depth of 100 meters and more. And we arrived to the conclusion that we have a very high porosity of the comet, and we confirms the result observed on the surface with a major contribution of organic material in the interior.
Yeah, and this is very important because unless you probe directly the internal structure, the only thing that can tell us about the internal structure is the density of the asteroid that we can measure with a spacecraft, and we compare it with the density of a meteorite analog. And the difference tells us whether there is void, if the density is lower, whether there is porosity, but that's very indirect. So the best is if you can really probe directly with some radars, for instance, what's inside, because this has a lot of implications about how they form initially, these bodies, and also how you can deflect them with an impact, because the internal structure has a very high influence on the impact response of the asteroid. And this has been done on a comet, but this has never been done on an asteroid. So with Hera, this guy will also perform the first direct measurement using a low-frequency radar. Can you tell us about that?
Yeah, the idea is to do the same, or quite the same on the Didymos system, using a monostatic radar on the CubeSat, on the Juventas CubeSat, to probe the internal structure and to retrieve information of the size, the typical size of the constitutive blocks. And it's crucial for this guy, in fact, because it's a way to better model the gravitational accretion and reaccretion of asteroid after collision.
Yeah, because one of the things is that we are going to visit a small moon of a binary system with Hera, and we want to understand how this moon forms. So we think it forms from the main body, but how does it work? We have some ideas, but we need to check with the internal structure. So that's interesting. And Hera is composed of two CubeSats, so the main spacecraft, and one of the CubeSats is called Juventas, and will carry this experiment. And in the NEO-MAPP project, oh, look at that, we have the French patrol. Yeah, hey, guys, you have the French patrol. So for NEO-MAPP, we organized the arrival of the French patrol close to the Promenade. So this is the beauty of this. All the time something happens. And this is the military people from the, let's say, the equivalent of the Air Force, who are passing toward Nice to say hello. It's always great to have them. And so in NEO-MAPP, we have also another radar in development, under study, because as Alain was saying, we have a low-frequency radar on Hera, which is a radar using very low frequencies, and then for that can go through the whole body. While in NEO-MAPP, because we want also to plan further away in time for other missions, we are developing a high-frequency radar, which is another kind of radar that can allow to basically measure in better details the subsurface of the asteroid. So we don't go through, but we have a higher resolution at subsurface, and this is also very interesting. So everybody is saying goodbye to the French patrol, and while we are doing so, we have Adriano Campo Bagatin from Alicante University, and Adriano was originally working on impact, including impact experiments, so he's also good at breaking things like me, but me is not voluntarily. And now he's doing some numerical models. So what are you doing, Adriano?
So, okay. We are interested in what happens in the interior of asteroids and comets, small bodies in general, because actually we know nothing of what is inside, so we try to understand by numerical modeling what is the internal structure. And okay, this is what we essentially do.
And the beauty is the fact that in this kind of project like NEO-MAPP, we combine the different approaches. Like, for the moment, we don't know what will be the internal structure of the asteroid. So the radar will probe inside. But of course, the radar will probe and give a signal, and we have to interpret this signal. So if first, numerically, we define some internal structure, and then we simulate the observation by the radar of this internal structure, then we can compare the signal to the real signal and see whether it matches. So basically, we built already a database of possible observations by the radar of the internal structure. And then when we have the real signal, we compare, and therefore we can know what is the equivalent internal structure. So that's why in space missions it's important to have a synergy between the models and the observations. Like for the impact, we predict what kind of crater size we will have and what it means in terms of what's below. And when we'll be there, we'll have the actual crater size, and therefore, thanks to the model, we can determine what is below the crater. So it's always a synergetic work, which is kind of complicated because we need to make sure that people communicate with each other and understand each other, knowing that instrument people have a different language than modelers. So we have not only to translate from Spanish to Italian to French, but also from a modeler language to an instrument language, which is actually fascinating.
You forgot to say something, that is that when models are not in accordance with observations, the observations are wrong.
Yes.
This is the typical theorist view.
Exactly. Yeah. We don't use experiments to validate the models. We use models to validate the experiments. Yeah, right. Good to know. Jean-Baptiste. So Jean-Baptiste is actually a French expert, very high standard expert, but he went through Germany. He went to Germany, but that's not his fault.
They didn't want me.
Exactly, that's a pity that we have great researchers who want to work in France, but then France doesn't want them because the number of positions is totally small, and therefore at the end many people go away, not because they want to go away. That's the worst thing. So it's a disaster. But anyway, welcome Jean-Baptiste. So Jean-Baptiste is a long time from the beginning in Hera and therefore NEO-MAPP. Tell us about what you're doing.
So thanks, Patrick. I'm working in Berlin in the DLR Institute for Planetary Research. And with NEO-MAPP, I'm working mostly on all the shape reconstruction and trying to look at new techniques to combine data from different instruments to get the full shape of the object that we are observing. And so we want to use not just images from the camera, but we want to combine this with the laser altimeter, with the radar, with everything we have, basically. And for Hera, I'm responsible for the camera on the mission. So we are taking the knowledge we gain from the NEO-MAPP project, and we try to apply it to Hera to design better trajectory for the spacecraft or better ways to acquire the data to maximize the science return of the mission.
Yeah, the importance of the shape model is very large because with the mass of the asteroid and its shape, then you get what we call the density, which is a mass over the volume. So you need an accurate estimate of the volume given by the shape. And that's what I was saying, that by comparing the bulk density of the whole asteroid to the density of meteorite, the difference can tell you something about the internal structure. It's another way to probe indirectly the internal structure. And one thing that we try to do with NEO-MAPP is not only to use a camera, but to have a multi-instrument approach where we, from different directions, we try to get data, and by combining these data together, then you check the consistency and you increase the robustness of your result. Like for the shape you can use the camera that gives you the dimension, etc. But if you have a laser altimeter, it gives you even more precise measurements, and you combine the two, and then you get your shape. So it's really great because we have a great team with people working on different instruments, and they combine that together. And Jean-Baptiste is already used to that because he worked on the Osiris camera on Rosetta. So he has a long time experience, and all the fascinating images you see from the comet Chury are actually provided by this camera. So I am of course, being the lead, I need to be very tall.
We have a meeting at 3 p.m. and
Yeah, exactly. So thank you very much for your time. We are super happy. We'll have a lot of surprise because all we do, many of the things we plan will be done, but maybe the prediction will be wrong, as always, because we go to a totally different world. We never went to such a small body like Dimorphos, which is only 160 meters in size. And I can tell you, having had the pleasure, and you also guys with a jury, to be the first to see images of 2 asteroids, Bennu and Ryugu, it's a feeling that cannot be described by word, because you really feel like an explorer of a new continent, which is 100 million kilometers away from Earth. And the first reaction is, oh gosh, it's all wrong. We all had it wrong. And that's great. That's a great feeling, actually. Yeah, it's challenging. Exactly. Yeah. These bodies challenge us all the time because they are in an environment that challenge our intuition, which is based on what we have on Earth. So we expect a lot of surprises. And when we have a good team, a cohesive team, we enjoy that together, which is also very important, because why we do that is because it's fun, not only because it's enriching in terms of knowledge.
And we have a fantastic team.
Exactly, we have a fantastic team. So stay tuned, you'll have a lot of news regularly, and thank you for listening to us and enjoying with us.